Hey there. For my problem, I'm doing 13.7e number 5, which is about finding the Taylor polynomial approximations of a given function, the first and second order Taylor polynomial approximations, the linear approximation L of xy and the quadratic approximation Q of xy. At this given point, 1, 3, for the function f of x is equal to x squared times y plus y squared. So I'm going to rewrite this a little smaller to save a little bit of space. These polynomial approximations give you a good approximation near the point. The first order Taylor polynomial is called the linear approximation because it creates a plane that approximates it with a line. The second order ends up adding in a little bit of curvature and concavity, quadratic curvature, with the second order, the second partial derivatives of your equation. And you want to use this to approximate your function. If your function is difficult to deal with, you can approximate near a point with a much simpler, this is a simple function here, but you can imagine there are more complicated functions where this could be really helpful. So the first thing that you might want to do is, if you're trying to approximate at this point, you're going to be building off this point, you want to evaluate your function at your given point. So this is 1 times 3 plus 3 squared, 9, 12. So our point ends up being 1, 3, 12. I'll leave that there for now. Well, I'm going to run out of room soon. So the formulas for these approximations are as follows, which I might have to reference my notes in a second so I don't get it wrong for you. But you start off with your evaluated point here. So your function evaluated at, I'm going to call these x naught and y naught. I think the book refers to them as a and b. That's very common. I like to use the x naught and y naught because it reminds me of other linear systems we use and other stuff that I've done. So it's kind of just helpful for me. So you evaluate at your point, and then you're going to add your slope information, your derivative information. So it's going to be f sub x, which is a function, of course, of x and y. Don't forget to write that. Heaven forbid. And then it's very similar to a lot of other lines and planes and stuff like that. X minus, this is your first derivative evaluated at your point, x naught, y naught, or ab, and then x minus x naught, plus your first derivative with respect to y of your function evaluated at your point, x naught, y naught, times this y minus y naught. Let me just double check that I got that right. This will give you your first order linear approximation. And notice that it has this, your point that you're evaluating at, the point that you're building your approximation off of. Your second order quadratic approximation, which, by the way, this L of xy is kind of only valid at our point 1, 3. So it could be imagined in some use cases that you might want to even put a little subscript to show that this function is an approximation near this point 1, 3. It should be depending on your function, there's going to be a region where it is an actual good approximation. As good as it can be for being a simple linear approximation. If you want to get a better approximation, you use your second order. I'm sure you could go further than that. But this second order approximation is going to build off of your first order approximation, and then you're going to do the fancy, why it's called Taylor. I assume, I don't know, I'm not a mathematician by any means, but you go ahead and put in your information about your second order. So that's f sub double x. So the second, your second partial derivative with respect to x of your function evaluated at your point over 2, and this similar x minus x naught formula here. You see that often, and then this ends up being squared because it's your second order Taylor stuff, math things. And then you add in your second mixed derivative, so your derivative with respect to x, and then differentiate it again with respect to y. It'll give you this middle term here, evaluate it at your point, and then it has this x minus x naught, y minus y naught, and then I have to go, this is all going to be part of the same thing, but you can also have this other term here, which has your second derivative with respect to y, second partial derivative with respect to y information in it, which is again evaluated at your point that you're approximating at over 2 y minus y naught squared. So you see there's these over 2 squared part, and then there's your mixed partial. And you see that it builds off the quadratic approximation is the linear approximation plus these other terms. So in order to find your quadratic approximation, you need to first find your linear approximation. So I'm going to go ahead and, for right now, erase this part because we need to do the first part first. And so there's a couple things we have to find. We have to find our first derivative with respect to x, first derivative with respect to y, and we need to evaluate them. And we already evaluated our function. So let's start with our f of x, f of course, f sub x, first partial derivative with respect to x of our function, which is a function of x and y, two variables. Very important that you write it all like this. No one would understand otherwise. So here's our function up here again. So we're taking a derivative, nice simple derivative, and then you take your partial with respect to y. It's very hard to do these things when you're on camera, it turns out. And then you can, using that information, build your linear approximation. So this evaluates to 12. Our function at the points that we have evaluates to 12. And then, for the sake of space, maybe I'll just assume you can follow along. 2 times 1 times 3 is going to be 6. And we have this x minus the point that we're evaluating at, which is 1. And then we are going to have this evaluated, so 1 plus 2 times 3, 7, quite possibly. Y minus the point that we're using, which the y is equal to 3. And then we can simplify this a little bit. It's easy enough. So it ends up being 12 plus 6x minus 6 plus 7y minus 21, which I believe ends up being equal to 6x plus 7y minus 15, which is your first order Taylor polynomial approximation at the point 1, 3, given the inputs 1, 3, you get this nice little plane that approximates it near this point. We're going to keep this down here, maybe in the corner. I'll even write. And this is our first order approximation. And I'll go ahead and rewrite the formula for our second order approximation, our quadratic approximation, because we got some squared terms in there, variables squared. Again, function of two variables, it's going to be your first order approximation plus your, forgive me, I stumble over this, it turns out. Doesn't really matter the order you write them in, but say it. Your second partial derivative with respect to x, so f sub x, x sub double x, evaluated at your point, x naught, y naught, over 2 times x minus x naught squared plus your mixed partial derivative, so f sub x, y, evaluated at the point, times x minus x naught, y minus y naught. And then also you have kind of the sister term to this with your second partial derivative with respect to y, evaluated at the point. I wish all this would fit better, but I need a bigger whiteboard. Oh, yeah, I got that square term. Y minus y naught squared. So we have to find a couple things here. We already have our first order. We need to find these second order partial derivatives. So these are pretty simple. This is, of course, a function of two variables. We're going to evaluate it. I'm sorry, we're going to take it. I already erased the... Ooh, now I got to think. How would I do that to myself? It's going to be 2y. I have it written down here. Do a little practice run. Yeah, it looks like 2y. Sorry, I shouldn't have erased the first, but you can figure it out. So we'll do the second partial derivative with respect to y, which is 2, yeah? Yep. And then this mixed partial ends up being 2x, yeah, 2x. So then we want to evaluate all of these at our point, because that's what we end up using, the information. So we'll just say, I'll write it all out. Maybe I'll write it out somewhere over here, so we can keep it on screen. So evaluated our second partial with respect to x, evaluated at our point 1, 3, is equal to 6, yeah? And then the second with respect to y evaluated at 1, 3 is a constant. And then that mixed one evaluated at 1, 3 is just 2 again. So then now we should have everything we need to put it all together. I'm gonna get rid of this for now. really need that, and I have no room. I'm gonna get rid of this too. You can just imagine that's there. You know it's there. Plus, here, I'll do plus dot dot dot. It exists. So then, our quadratic approximation evaluated at the point 1, 3 of, this is of course a function of x and y, our second order Taylor polynomial approximation. We're going to start with our first order because we need that. Notice that this doesn't have, like the rest of this, doesn't have a point built into it, like the function evaluated at this point. That information is held in your first order. So you start with kind of that point, you build a plane off of the point to approximate it, and then you can add some curves into it. And that's what the second order part. So you start with your first order part. And then you add your second partial derivative with respect to x evaluated at the point over 2. So 6 over 2 is 3. And then x minus your point 1, or at the x that you're evaluating at for your point that you're approximating near. That squared. And then you want to add, I don't know if I want to put it on this line, but I'm going to try. Your mixed partial evaluated at the point, which was this constant function, times x minus x naught, y minus y naught. And then you're going to have that, the sister term to that, so it's, one of these was a constant function. I think this was a constant function, and then this one was actually evaluated as 2, but sorry. The constant function over 2, so it ends up being over 2. 2 over 2, 1, I'm just going to ignore that. So it becomes y minus 3 squared. And there is a simplification of that. I think this all checks out. The online textbook has a simplified version available. I'm going to go ahead and leave it up as an exercise to the reader. It would be a lot of fun to simplify that. There's so many different ways you could do it. Who doesn't love that? But that is the fundamentals behind these, at least the first and second order Taylor polynomial approximations with functions of 2 variables. I imagine you could probably do similar interesting things with more variables, and even go for a third order, fourth order. And again, I mean, the most important part, it's only going to be a good approximation near the point that you're working with. And for a function like this, there's no reason to do it. But there are functions that are harder to deal with that you might have numerical methods to approximate them at a point. This is one of those methods where you can kind of get something that will be a correct enough answer for whatever you're trying to do. And it's not going to be the perfect answer or the exact answer, but it's going to be a heck of a lot easier to work with just simpler things, because you end up just having like a quadratic term. You don't have to have crazy things, because sometimes your partials can turn into like complete monsters, and you end up just evaluating them at a point where if your function is a complete monster, your partials, everything is a monster, but you just evaluate it at points, and then you square the terms. So it ends up being really nice and easy to deal with. Thanks.